We'll now turn to applications of connectivity or connectedness. Okay, as mentioned right in the beginning, this is a topological property, and a typical topological theorem is the intermediate value theorem. What we'll prove is a generalization of it, which fairly easily includes the classical statement. We won't literally prove the classical statement. So the first part of this is the following proposition. Or maybe I should have a caveat before the proposition. So we allow plus minus infinity just here for n points of intervals a, b, etc. We'll consider half open, closed, etc. Infinity means it has to be open at infinity. So intervals we allow plus minus infinity, and for infant soup. Okay, infimum and supremum will be allowed for the present, just for this segment. So let's note the following. I might as well call it a theorem because the statement is quite nice. Namely, a non-empty set inside the real numbers, let's call it A in R, is connected if and only if A is an interval. Okay. So the proof is we have seen intervals are connected. Intervals are connected because if they are open on both ends, whether they are finite or infinite, they are homeomorphic to R. Otherwise, they are closures inside themselves of the corresponding open interval where we eliminate endpoints. So this is quite easy to see. We have seen this already. So now the converse, which is not hard either, but is interesting. Conversely, so suppose A is connected. The main task is to find little a and little b. Okay, and A is non-empty. If it's empty, well, it's an empty interval if you wish, but suppose it's connected and it's non-empty. We let A be the left end point, which is that we just look at infimum of A, and B equals sup B. Okay. Now, these may or may not be in the sup of A again, the set A. I'm going to rename this J because J, it's going to be an interval. So here we are, J, if and only if J is an interval. We look at infimum of J and the supremum of J. They may or may not belong to J, and whether we get open or closed depends on that. So the main lemma here is that if A is less than or equal to C is less than B. So if C is a number, then C belongs to J. And the proof is almost identical to what we saw for the rational numbers and similar to what we saw for the Cantor set. Otherwise, J is going to be J intersection X in R, X is less than C, disjoint union with J intersection those points in R such that X is greater than C. So we look at these two rays. Both of these are open in J because the side out here is open. So this is open in J and this is also open in J. So J is the disjoint union of two open sets, a contradiction. Okay, so thus what we have is C belongs to AB implies that C belongs to J. That is, the open interval AB is contained in J. Okay, also J is contained in the closed interval AB. Okay, where we could be closed at infinity doesn't mean we really include AB. So let me write that as a set instead. Set in R such that A is less than or equal to X is less than or equal to B. Okay, so if A could be minus infinity, B could be plus infinity, in which case the less than or equal to automatically means less than. We are looking at real numbers. It follows that J is an interval. Since there are only one possibility, we might as well spell them out. There are four possibilities. A, B. It could be closed at A and open at B. It could be open at A and closed at B. And it could be closed at A and closed at B. And the closed part has to be finite, only then it's there. But these are all the possibilities in any case. So in any case, we have an interval. So what we, which case we have depends on whether the infimum is realized or the supremum is realized. We know that anything strictly between the infimum and supremum is in J, and anything in J is weakly between the infimum and supremum. So we can deduce immediately that we have four cases, sometimes less than that if one of these is infinity, but in any case we always have an interval. Okay. This more or less gives us the classical form of the intermediate value theorem, which I won't state in its classical form, but instead state as a corollary. If f, first f(x) is connected and f maps x to R is continuous, then we know that f of x, this contained in R, is an interval. And even more classical form, corollary of the corollary, if J contained in R is connected. So I don't need to say that, that's hardly worth it. If A, B are in R and A is less than B, this is where we have intermediate value theorem, then and f maps, well, it could be all of R, but AB is enough. AB to R is continuous. Then f takes all values between A and B, but another way of saying it is f of AB is an interval. Okay, so hence C belongs to f of, well, it could be ordered in the either direction. Okay, so the corollary I will assume is easy to interpret. So this is the intermediate value theorem. We have seen this in the general topological form. So if I take any connected set, its image is an interval. So it takes all values from its lowest to its highest. So if it takes two given values, we know it takes two given values. It takes everything else. Okay, so this was our first application of connectivity, justifying our topological properties.